Right. Well, we want to try to understand moment generating functions a little bit better. So here in this problem, we are given a moment generating function, and we're told that our random variable is discrete, it's non-negative, and it's integer valued. All of that's really important. And all we're given is the moment generating function. And from that, we're asked to find the mean, the variance, and this particular probability. So I want to review some of the key facts that we're going to use. We're going to use the fact, oops, let's use a different pencil here. We're going to use the fact that the moment generating function, the first derivative of the moment generating function, evaluated at 0 is the mean. And we're going to use the fact that the second derivative of the moment generating function evaluated at 0 is the second moment for x. And so that's how we'll be able to solve the mean and the variance, and then we'll come back and talk a little bit more about how to get the last probability. So to solve the mean, we're simply going to take the first derivative. So I'm going to drop the x subscript and just write m prime of t here, and I'm going to get what? A sixth, and that actually goes away. 6 times 1, the 1 is 0, so I'm going to get a third e to the t plus, I'm going to get a half, and then a 2 is going to come down and cancel that, so e to the 2t. So I get this function. I'm going to plug in 0, so m prime of 0 is a third plus 1, which is 4/3. So just like that, I've got the mean. The mean is captured, the mean of my random variable is captured by the moment generating function. And now when I want to go for the variance, of course I need the second derivative. And so I get a third e to the t plus 2 e to the 2t. I'm going to plug in 0, and I get a third plus 2, which is going to be 7/3. And that's the second moment. It's not the variance, it's the second moment, but I now know the variance that I'm after, the variance of x, is going to be the second moment minus the first moment squared, 7/3 minus 4/3 squared. And when you combine that, you should get 5/9. So we know the variance is 5/9. So the moment generating function, even though it doesn't tell me all the different probabilities, right? It's not the probability density function. It still captures all of the key information about my distribution. And in fact, in the discrete case, it actually captures those probabilities as well. So let's tackle the last part. And to do that, we want to remind ourselves the formula for this. So the formula for the moment generating function in general is that it is the mean of e to the t times x. And in the discrete case, right, we sum, because it's discrete, over all values of x. And so we are integer valued. We're non-negative, so we're starting at 0. So this is x equals 0 to infinity. And right, when you take the mean of a function, it's that function, so e to the tx times the probability function p of x. Well, this is exactly the part that we're missing. We weren't given the probability density function, and yet when you're given the moment generating function, you actually are given everything you need. And so let's think about this. The moment generating function, I can write this out. This is going to be e to the t when x is 0, so e to the t times 0 times the probability of 0 happening, plus e to the t when x is 1 times the probability of 1 happening, plus e to the 2t times the probability that x is 2, plus e to the 3t times the probability that x is 3, plus so on and so forth. Right? You have this technically infinite sum here, and we realize that our let's clean this last one up here. E to the t times 0. This is just a 1. So this thing is really just a p of 0 plus e to the t times p of 1 plus e to the 2t times p of 2. And if you look back at our MGF, we stopped at e to the 2t. So that's actually all that we need. We don't need to write the other terms. In fact, we know what those probabilities are. We'll get to those in just a minute. So this is equal to our function, and our function was 1 over 6 plus 1 over 6 times 2, so that's a third e to the t plus a half e to the 2t, and all of a sudden I can tell you the probability that x is 0 is a sixth, because that's the constant term, and the constant term is p of 0. I can tell you the probability that x is 1, and that's going to be 1/3, because that's the constant times e to the t. And I can tell you the probability that x is 2, and that's going to be a half. And in fact, you can tell me the probability that x is n, that's 0 whenever n is greater than or equal to 3, because there are no more. They're zeroed out. And so now when we want to talk about the probability that x is less than 2, then I'm simply going to get, it's less than or equal to 2, I believe. What do we write? I wrote, we'll do less than 2. So less than 2 is going to be a sixth plus a third, which is exactly a half. All right? So that's how you can work those out using the moment generating function.